What determines the perfect shot? Every basketball shot, every penalty kick, even fireworks. There's physics behind them all. Welcome to projectile motion. It's not just one motion, but it's two. Gravity pulls things down, while the initial push drives them forward, creating the iconic curve. From balls to satellites, projectile motion is everywhere. By the end of this lesson, you will predict every landing point. But students, before we start, don't forget to like, share and subscribe to our channel. Let's learn together. Hello students, today's class is about projectile motion. Projectile motion is a very important category of motion in which many direct questions are asked. So you should be very thorough with the concepts as well as the associated formulas. Alright, so shall we start? Now, projectile motion, when I say that, so you should first understand what is a projectile. So a projectile is basically any body that is projected, but then it is moving under the influence of gravity alone. So, for example, a football that is kicked, a catapult, a cannon shot, all these are examples of projectile motion, because once they are projected, then it is only gravity that is influencing them. Maybe there is one more force of air resistance which is very prominent, but we will take into account that also, but only qualitatively. So I mean the formulas and the quantitative analysis we will only be doing for projectile in which air resistance is not included. So I think it is now very clear what are we going to study in today's class. Today's class is going to be about projectile motion. You can just quickly write one line definition. Projectile motion is a type of motion experienced by an object that is projected and moves under the action of gravity only. You may write that. Next, we will talk about projectile motion in two parts. So the first part that we are going to take is the horizontal projectile motion. So when I say a horizontal projectile, that means something that is projected horizontally. So the initial velocity that is imparted is entirely in the x direction. So now you should understand we are beginning with motion in two dimensions. So till now majorly our discussion was limited to motion in one dimension, but now we will simultaneously handle two dimensions. And what are those two dimensions? So it is very obvious that it is the x direction and the y direction. X direction we always take rightward positive, and y direction we always take upward positive. Okay, so you should have that in your head that we are going to begin with motion in two dimensions, and we are starting with the motion in x direction y because we are projecting it horizontally. Since it is the starting velocity, we are denoting it by u. Let's say the motion starts here, t is equals to 0, let's call this point A, and then it reaches the ground here, and let's say this point is B. Okay, so starting here, ending here, this is the range covered on the ground. Since we are projecting it horizontally, it is very much recommended that we start off from a greater height so that we have some time to elaborate the motion. So that is why we have chosen a building here, and we are projecting it from a building, a very tall building, and then we are analyzing the motion while it is falling on the ground or striking the ground. Now, motion in two dimension would be very easy for you if you maintain one discipline that at a time you have to analyze motion only in one direction. So for example, if I may write that initial velocity in the x direction is going to be u, initial velocity in the y direction is going to be 0. Why? Because entirely we have projected this in the x direction. X direction, the acceleration is going to be 0. Understand why? Because we are talking about gravity here. So it is moving under the influence of gravity, which obviously acts only in the downward direction. So right now we are only considering gravity that is acting in the downward direction. So will you be able to relate with this, that acceleration is in y direction but it is negative g because it is acting in the downward direction, and since we've taken upward positive, so gravity will be negative. You can write this down first. Next, we have to talk about a lot of things here. So the first thing that I want to predict is the time for which the ball was in air. So what I am going to do is, I am going to one by one choose on to which equation of motion I have to use and in which direction I have to use that. So let's say I am starting off at A and ending at B. We will assume that the height of the building is given to us, let's say h, and the initial velocity is also given. So what is the given data? Initial velocity u and the height h. So shall we start? So we would write, let's say, second equation of motion, s is equals to ut plus half at square. While I am doing that, you can clearly see I am writing a y in the subscript so that it will be very clear to all of you that we are writing or using the equation in the y direction. So what is sy? Are we able enough to understand that if we started off here, let's call this coordinate 0, 0, then this coordinate is going to be r minus h. Since we have moved a distance r in the x direction and we have receded, or we are going down by a distance h, so we are writing it as negative h. So what is our displacement in the y direction? It is negative h. Now what is uy? So uy is going to be 0. Refer to this and life would be easy here. What is ay? Ay is negative g into t square. So I have just used the second equation of motion in the y direction. This gives me the value of time as under root of 2h by g. So this is the expression for the time of flight. Very clear, it does not depend on the starting velocity. It does not depend on the starting velocity. So it doesn't matter if you throw the ball with more speed or less speed, as long as it is the same building, it will land at the same time. The only difference is going to be if you throw it with a more speed, then it will land further away, but the time it will take to strike the ground is going to be the same. Okay, please note it down. You can pause the video also and note it down. So we have first calculated t, which is indicating the time of flight. All right. So what is the next thing that we wish to talk about? So the next thing we wish to talk about is, let's say, the range. Is the range. Okay. So what do you mean by range? Range is basically the horizontal displacement, or the displacement along the ground, how far the ball will fall, how far the projectile will fall. That is the range. So again, we are using the equation of motion from A to B. We are using the equation of motion from A to B. Okay. But which equation are we using now? Second equation in x direction. So this time we have changed things and we are using second equation but in x direction, since we already know the time now. So Sx is going to be r, that is the range. Ux is going to be u, that is the initial velocity in x direction, that is u. Time is going to be t. Can we say this term will become 0 because there is no acceleration in the x direction? So range will turn out to be u times under root of 2h by g. U times under root of 2h by g. Very clear. Range will depend on two things. U, that is the initial velocity, more the initial velocity, more the range. Second, height of the building. So more is the height of projection, more will be the range. Can you understand why? Because you will get more time. The projectile will get more time to fall. Okay. You can copy this down. So we've covered the main two aspects, the time of flight and the range. Shouldn't be a problem. it's not that you have to mug up the formulas, but you should have the understanding for doing any problem, mathematical problem related with this. So you write it down and be very clear how I'm using the equation. I am deciding which point I'm starting, which point I'm ending, and I'm deciding which equation I'm using and in which direction I'm using that. Copy this down, then we will move forward. Okay, next I want to talk about again horizontal projectile. So you would say, what are we talking about now? We have calculated the time of flight, we've calculated the range. One thing that I want to talk about is the speed of striking. So you all know that we started off with a velocity u only in x direction. We landed here. One thing that you all should understand by now, that in x direction motion is uniform. Motion is uniform. So its x velocity never changes. So we started off with some value of u, it will maintain that value. Why? Because we are not considering air resistance. But what about y velocity? So you would say that y velocity will start appearing, let's say like this, then this, then this, then this. So y velocity is continuously increasing. Why is it increasing? Thanks to gravity. Okay, so shall we write now what is Vx? So you would write ux plus axt, but since ax is 0, so Vx is going to be u itself. So x velocity never changes. What about Vy? You would write Vy is equals to uy plus ayt. Vy is equals to uy plus ay into t. What is uy? 0. Initial velocity was purely in x direction. Again reminding you. What is ay? Minus g. And what is the time? Under root of 2h by g. So what is the value of Vy that we are getting? So we are getting minus root 2gh. It's not that you have to mug up the formulas. I'm again reminding you have to understand why are we making this particular choice of equation. So this is Vy, this is Vx. You all know that Vx means in x direction, Vy means in negative y direction. So for the net speed, here, whatever is the net speed here, we can say that it is going to be vector addition of these two. So it is going to be under root of u squared plus root 2gh whole squared. Okay, according to the Pythagoras theorem. So it is going to be u square plus 2gh, and let's say it strikes at an angle theta. Then this theta with the ground you can calculate using tan theta. So tan theta is going to be Vy over Vx, that is the y velocity over the x velocity. So that is going to be under root of 2gh divided by u. That is the angle of striking. Theta is the angle of striking, and this is the speed of striking. So I think you have a basic idea now how projectile is functioning, and you can very well now understand how you have to divide everything in x direction and y direction. You can pause the video, think about it, re-watch the video just to understand things again, but it should be very clear to all of you. Only then we will move forward. So next what we want to talk about is oblique projectile motion. This is something you can relate with even more. Why? Because you have all played football or some kind of sport, and many sport would involve this kind of trajectory. So this trajectory, this curved trajectory is basically parabolic in nature. So this trajectory is parabolic, but this is not the correct trajectory when you talk about real life, because in real life even air resistance has to be taken into account. But right now we are only discussing without air resistance. Okay, so one more time, it is u projected at an angle theta with the horizontal. So this time we are projecting it obliquely, hence the name oblique projectile. Okay, you projected at an angle theta. I have assumed theta with the horizontal, theta with the horizontal. Okay, so now you need to take help of vector resolution here. Again the same convention, rightward positive, upward positive, and then what we are going to do is we are going to have velocity this time even in x direction and in y direction. So what is the velocity in x direction? So let me use red color here. So it is going to be u cos theta. And what is the velocity in the y direction here? It is going to be u sin theta. Since you already know vector resolution, so this is u cos theta and this is going to be u sin theta. Please make a note of this, u cos theta and u sin theta. So we've projected it horizontally with u cos theta and vertically with u sin theta. Make a note of this. Alright, so x direction, the velocity is u cos theta. Since this is going to be the base and this is going to be, this is going to be the base and this is going to be the perpendicular. So this is u cos theta and this is u sin theta. So the y direction velocity is going to be u sin theta. So this time we have started the motion in x also and in y also, but we are projecting it upwards. What is the acceleration again in the x direction? It is going to be 0, and acceleration in y direction is going to be negative g. Let's call this point A. Let's call this time t is equals to 0. Then this is the highest point. Let's call this B. And this is the final point. Let's call this C. Finally, the time, we call it as the time of flight. Okay. So now you can visualize clearly the journey has two parts. From A to B, the projectile is ascending, and B to C, it is descending. Ultimately, it lands back on ground. So we can call the coordinates of this as r comma 0, where r is the range. Okay, if we start off with 0 comma 0, then this coordinate is r comma 0. Similarly, we will prove it. The coordinate of this is going to be r by 2 comma h max, maximum height. So r by 2 basically implies that this is very symmetric in nature, and this point is just above the midpoint of A and C. So B is just above the midpoint of A and C. I think we can start now. So we will first start with the time of flight. So we will start with time of flight. So time of flight, you would understand, it is the motion from A to C. It is the motion from A to C. A to C. Now, which equation are we using? Very quickly, S is equals to ut plus half at square. That is the second equation of motion precisely in y direction. Now, what is Sy? It is 0. Why is it 0? Because we started off from ground, we land back on ground. We might have moved a distance in x, but in y our displacement is going to be 0 because it is ground to ground. Ground to ground. What is uy now? U sin theta. All right. T plus half ay is minus g times t squared. So t turns out to be 2u sin theta over g. Okay, this is the time of flight. You can also write it like this, 2uy over g. Are you able enough to understand this? Because uy is nothing but the initial velocity in y direction. So this is giving us the time of flight, the time for which the projectile is going to be in mid-air. Okay. Next we should talk about, let's say, maximum height. Next we should talk about maximum height. But before we even start with that, I want to know what is the time here. What is the time here? So, can we all understand that in x direction, velocity will never change? In x direction, velocity will never change. So, if I am indicating it with the red arrow, So this red arrow will never change. X direction, the velocity is going to be u cos theta always, because in x direction there is no acceleration. So x direction velocity is the same, u cos theta. It never changes, okay, even till the end point. But y direction, the velocity is definitely changing because of gravity. So shall we talk about that now? So let's say y direction, first the velocity is decreasing. Why? Why is it decreasing? Because gravity is acting opposite to the direction of motion. So we projected it upwards, gravity is downward. So that is why this velocity is getting smaller and smaller, and ultimately at this very point, at the highest point, y direction velocity becomes 0. Y direction velocity becomes 0. So can we use that now? From A to B, if we apply v is equals to u plus at, then we do know that highest point, y velocity becomes 0. It is taking a u-turn at the highest point. So it is going up from A to B, then it is coming down from B to C. So uy is u sine theta and ay is negative g. So this time, let's call it ta, that is the time of ascent. So this time turns out to be u sine theta over g, or uy over g. Copy this down, copy this down. So if you've done that, you must be realizing that this time is just the half of this time. So what does that mean? That means A to B, it just takes half the time of what it takes from A to C. That means A to B, the time of ascent, is equal to the time of descent from B to C. So we can say the total time is equally divided in the ascent part and the descent part. Okay, so this is TA, and therefore this is also equal to TD. So TA equals to TD is equals to T by 2. That explains why B should be the midpoint of A and C, because X direction it is uniform motion, so half time it would have covered half the journey, right? But why did we discuss all this? Because we now will be using the fact that at highest point Vy is 0, and if we may write Vy square is equals to Uy square plus 2Ay Sy, that is the third equation in y direction, then that can give us the displacement in y direction, and that is what we are wanting to find out. So what is Vy? It is going to be 0, because we are writing equation from A to B. Keep that in mind, what points we are taking as reference. Now what is Uy? It is u sine theta. What is Ay? It is minus g. What is Sy? So let's say that is h. So h turns out to be u square sine square theta over 2g. U square sine square theta over 2g. That is the maximum height. So we've talked about maximum height, we've talked about the time of flight, and now you all should know time of ascent is equal to the time of descent. Please copy this down, then we'll move forward. Okay, next thing, again we want to talk about projectile motion, but the next thing that we want to talk about is the range. So range is this distance. So you all would know that there are two things here. It is the displacement in the x direction. So we are going from A to C. So this was our point A, this is our point B, and this is our point C. We started off with velocity u at an angle theta. This is u cos theta, and this is u sine theta. So A to C, what are we using? S is equals to ut plus half at square. But in which direction? X, because we are wanting to calculate the horizontal displacement. That's why we are using the x equation. What is that displacement? R, that we have to find out. What is ux? Let's keep it ux. And what is the time? T. So here the time is t. But this ax term is going to be 0 for now, because x direction we are not considering any wind, any air resistance. So the range turns out to be, time of flight was 2uy over g. So the range turns out to be 2ux uy over g. Range turns out to be 2ux uy over g. In fact, if we go back to the previous slide, we can also write this h max as uy square over 2g. Can we do that? Because u sine theta is nothing but uy. So you can also write h max as this. Okay, so here the range is written as 2ux uy over g, which you can then write ux is u cos theta. We already know that. Uy is u sine theta over g. So the range turns out to be u square 2 sine theta cos theta over g. Okay, this is the value of range. Now there are two things, one identity of trigonometry that I want to use here, that is 2 sine theta cos theta, that is equals to sine 2 theta. So this is a double angle property, that 2 sine theta cos theta is equals to sine 2 theta. So I can write the range as u square sine 2 theta over g. Range I can write as u square sine 2 theta, not sine square theta, sine 2 theta over g. That explains one more thing. What if, which is very much something that you can easily relate with. What if you want to project something as far as possible? That is, you want to maximize your range, maybe some missile, maybe some football kick, you want to maximize your range, a javelin throw. So you would say range will be maximized when sine 2 theta achieves its maximum value, which you all know is 1. So that is going to happen when the angle, that is 2 theta, is going to be 90. So that means theta is 45. Keep that in mind as well, that you achieve maximum range. Automatically you will do that when you project something at 45 degrees. So when you do that, the maximum range will turn out to be u square by g. So we are assuming that for a given speed of projection, range will be maximum for 45 degrees, and that is going to be u square by g. Please note it down, the maximum range. Okay, so this is the general formula of range, and this is the maximized range you can have that will happen at theta equals to 45. In fact, you can talk about one small thing here as well. What is that? I will not take much of your time on that, but just one brief discussion. First you copy this down, then we'll talk. So what is that? What if you project something at a complementary angle? So let's say this angle theta was 60 degree. Hypothetically, this theta was 60 degree. What if you project something at 30 degree? So let me trace the path to you. It's going to be somewhat like this. What are you seeing? What are you observing? The white path and the blue path. You will see that both have the same landing point. So the range will be the same. Can you prove that? What if theta is replaced by its complementary angle? So complementary angle, I hope your concept is clear there. 60 complementary angle will be 30. 40 complementary angle will be 50. So you're projecting at an angle complementary of the previous angle. Okay. So in that case, the new range is going to be u square 2 sine 90 minus theta into cos 90 minus theta over g. And as you know, sine 90 minus theta is going to be cos theta, and cos 90 minus theta is going to be sine theta. Let's call this r dash, the new range. Then you would realize that the new range is going to be the same. How? Because sine 90 minus theta becomes cos theta, and cos 90 minus theta becomes sine theta. So here it was sine theta into cos theta, here it is cos theta into sine theta, ultimately giving you the same value. So the new range is going to be the same as the previous range, but only the range, not the path. Path is different, the maximum height attained is different, the time of flight is going to be different, but the range is going to be the same. Okay, so this is a very important fact. You can just keep that in mind. Two highlights here. First, that range is maximum for angle of projection 45 degree. Second, for complementary angle, for complementary projection, the range is going to be the same. Please note it down. Okay. Next, I wish to draw the associated graphs. And it is going to be very easy since we have already had a class on graphs. So we are wanting to quickly draw the graphs here. Okay, before in fact we do that, I hope you are very clear that y direction velocity was decreasing, and after B it became negative. Okay, so A to B y velocity is reducing, and then B to C y velocity is increasing but in the negative direction. All right, so now keeping that in mind, we can plot the graphs, I think. So first graph, one by one you anticipate the graph and then you match your answer. So horizontal velocity graph should be a straight line. Why? Because its value never changes. X direction, it is uniform motion. Vertical velocity, we started off with u sine theta at A. At B it becomes 0. If you can memorize this diagram, this was A, this is B, and this is C. Okay, so we projected at an angle theta, it will symmetrically land back at theta. We start off with u sine theta in the upward direction, it will land back with u sine theta in the downward direction, and at this point Vy is 0. So that is why it is a straight line. Why? Because the gradient is constant, acceleration is constant. You can associate this with the concepts that we have discussed in the previous classes. Then is the horizontal displacement. So horizontal displacement is again going to be a linearly increasing graph. Why do I say so? Because horizontal velocity is constant, so the gradient is constant, so it is continuously increasing with a constant gradient. Then is the vertical displacement. Okay, let's you try it first, then you match your answer. I think it should be like this. Why? Because initially the gradient is more, at B point the gradient becomes 0, and finally the gradient becomes negative. So vertical displacement, it's not going to be a straight line because y direction velocity is not constant, so the gradient cannot be constant. That is why it is a first decreasing gradient graph, then it is a increasing gradient in the negative direction. Okay, so these graphs are very important. We have always tried to draw the associated graphs with many questions that we do, and projectile you can sometime only get questions on graphs. So you should be very clear about these graphs. I will wait, you can copy these down. So we will end today's class by doing a qualitative analysis while even air resistance is taken into account. So you can clearly see now we are including the drag force, that is the force of air resistance. And there are two main things that you need to know about air resistance. First, it is always opposite in direction to the direction of motion, which you can clearly see by the red arrow. The drag force is acting opposite to the velocity. Second, it increases with velocity. So objects traveling with more speed will have to suffer more drag force. Okay. Now therefore you are seeing two different paths. One path is this and the other path has a shorter range. What do you think? Which one is the path when air resistance is taken into account? I think it should be very clear that this path is without air resistance. This path is without air resistance, while this path is with air resistance taken into account. So keep that in mind. You can clearly see this is without air resistance, the path we were discussing so far, which was parabolic. Now this won't be parabolic exactly, and the path will have a shorter range. So let's say the new range is r dash, and the new maximum height is, let's say, h dash. So h dash will be less than h this time. H is the maximum height without air resistance, and the range will also be less than r, that is r dash will be less than r, which is the range after air resistance is taken into account, and this is the range when air resistance was not taken into account. So we will just do the qualitative analysis because the mathematical interpretation here will be very complex. Similarly, the time of flight also we won't comment because it depends on the initial situation of projection. So keep this in mind, that what happens when air resistance is taken into account, that's only the qualitative analysis you need to know. You don't need to calculate the value of the range and maximum height when air resistance is taken into account. So we'll end today's class here, but we have only talked about the basic theory and the formulas involved, and in the next class, which will be a follow-up class after this, we will only do many numericals, including all these concepts that we have learned today. So don't assume that the projectile motion is completed here. It will only be clear when you will do the numericals, or we will discuss the numericals here. But that's all for today. Thank you.
If you enjoyed this video, please don't forget to like, share and subscribe to our channel.